Hello and welcome back. This is our next lecture in the continuing series of simulating neurobiological systems. This is Systems 556 or 750, taught at the University of Waterloo in the fall term of 2021. And today we're going to talk about symbols, or perhaps better, to be a little bit more technical, we're talking about symbol-like representations. What in the world do I mean by that? So far in the course, we've argued that we're trying to make models of brains. We're trying to figure out how brains work. We're trying to figure out what the algorithms are that are underlying cognition. And we've shown sort of from somewhat first principles that the things that groups of neurons are really good at doing are representing vectors, and that connections between groups of neurons are really good at computing functions on those vectors. And recurrent connections allow you to compute differential equations on vectors, which is great and awesome. There's all sorts of things that we can now do with that in terms of things like motor control or sensory processing or sort of really simple memory stuff like the keeping track of your location example in the little critter brain that we built. But it seems like it's really far away from like human cognition. Like, when people talk about human reasoning and what human brains do, so much, we start talking about language, we talk about reasoning, we talk about logic. And traditionally, the way that that's been modeled and thought about and simulated is something very AI-like, something like symbol manipulation. And there's been, in the history of cognitive science and in the history of trying to understand cognition, there's been a whole bunch of different ways of sort of representing this sort of thing. So you might have, like, how do you represent the idea that the number 9 comes after the number 8? I guess my example is backwards. So you might say, so this sort of formulation here is successor 8, 9. So this is sort of one way that people have sort of tried to write down in logic the idea that 9 comes after 8. So we're saying this is a successor, this is a property of two concepts. One concept is 8, another concept is 9, and we're saying that the relationship between them is that 9 is the successor of 8. Okay, and you could build up a whole bunch of big logic systems like that. You could think of sort of statements like all dogs chase cats. If you want to do that as sort of in a logic form, one particular way that one might do that is you could say that, all right, if X, whatever that is a dog and Y is a cat, then that allows you to reason across for any X's and for any Y's. That would allow you to reason that, okay, that X chases Y. And so, and people have done some very interesting jobs of building up very large databases of sort of common sense reasoning and sort of ways of encapsulating all sorts of background knowledge in this sort of form, and shown that it can sort of map onto at least some aspects of how humans reason. These sorts of things can even be sort of nested and structured. So you could say that you want to be able to represent a statement like Anne knows that Bill thinks that Charlie likes Dave, like some structured, complicated thing like that. So you need to be able to start having these things be components in each other and sort of build it. Okay. So that's sort of the classical AI approach to representing knowledge. It seems like it's sort of like the only game in town. This is how, this seems like, if you want to do any sort of thing that starts talking about sentences and reasoning and things like that, you've either got to at least do sentences, in which case you've got concepts and words and you've got grammar and things like that. Or if you want to do something that sort of attempt to come up with some sort of more fundamental, this is sometimes called like trying to find the language of thought. So what is the internal representations that reasoning takes place over? These sorts of proposals have been around. And all of this doesn't look anything like vectors and functions on vectors. And like something is very different here. Okay. And indeed, this sort of question of, well, hey, look, we're going to be trying to understand cognition. If we want to have a neurally based theory, if we want a theory of cognition that grounds out in neurons, we're going to have to say something about how these sorts of symbol manipulation type things are being done in neurons. If we switch over to the course notes, the lecture notes a little bit, there's a couple interesting, or one formulation of this challenge was from a book, a 2002 book from Ray Jackendoff, Foundations of Language, Brain and Meaning, Grammar and Evolution. Very interesting sort of foundational cognitive, cognitive neuroscience and cognitive science and its relationship to language. And in particular, he highlights 4 particular challenges, just to sort of show different aspects of this problem. So any theory that comes up with, how does language happen in terms of neurons is going to have to deal with these sorts of questions. So one of them, the binding problem, which is, all right, suppose you see a red square and a blue circle. Somehow in the brain, you need to now associate the concept of red with squareness, and the concept of blue with the concept of circle, and you've got to keep those two things separate somehow. Okay. So that's one interesting. How are we going to do that? There's also the problem of 2. Consider the sentence: the little star is beside the big star. So, like, suppose you'd solve the first one. Suppose you've got, okay, I know how, here's how we're going to have neural representations of red, neural representation of square, fine, and how to structure things. Suppose you've got a neural representation of star and a neural representation of star, and this representation of star needs to get associated with little, and this representation of star needs to be associated with big. We got to deal with that problem as well. How do you keep those things separate? And not only are you keeping them separate, but then you also have to say that, okay, and they have this relationship, that the 2 of them are beside each other. Okay. We also have the problem of variables. What's that? That is, there's some things that make sense to do and some things that don't. So it's sort of, I can say, so it's not these symbols, sort of bigness and starness, big and star and little and square and red. There's restrictions on how they can interact. I can say that there's a blue star. I can't say there's a blue little. How are we limiting things in that way? And then there's also this issue of working memory versus long-term memory, in that I can both use a sentence and I can remember a sentence. So I need some way of both representing, so some sort of representation perhaps while I'm using it, some sort of representation that lets me sort of store it for a very long time. Okay, it's probably maybe not a language-specific problem, but it's certainly one that is going to, whatever it is that these neural representations are, I'm going to need to be able to have that neural representation. I'm going to need to be able to store it, and then need to be able to recover it. Okay. So those are sort of big challenges, and in sort of this sort of 2002 time frame, there really wasn't very clear answers to these sorts of challenges. Lots of different interesting attempts. I'm going to sort of briefly sketch out some of the attempts just to sort of lead us into where we're going to hit. So one attempt in this direction is the idea of neural synchrony. This is sort of a very pervasive idea. It's come up at lots of different times in lots of different situations when trying to think about how brains work. And the idea is going to be, okay, suppose I have groups of neurons for each concept. Okay. So I have a group of neurons for dog, I have a group of neurons for cat, I have groups of neurons for, I don't know, different people, for thinking, I don't know, like just groups of neurons for different things, and maybe they're even at sort of different levels of abstraction. I might have a group of neurons for animal, a group of neurons for human, a group of neurons for furry. Okay. And then the idea is going to be that if I want to indicate that, say, a dog is chasing something, right, then I might have my group of neurons for dog and my group of neurons for a thing that chases, right? They might fire at the same time. Okay? That these two neurons fire at this, or if these two groups of neurons fire at the same time, that can say a dog is chasing. And if these two groups of neurons fire at the same time, that can mean that a cat is being chased. Okay. And they could like alternate back and forth. Okay, so that you might have these ones firing, and then these ones, and then back to these, and then back to these, and back to these, and back to these, and that could, take this sort of, so that would sort of bind these things. This is a dealing with the binding sort of problem. Similarly, I could have, say, neurons for circle and neurons for blue, and they'd fire at the same time, and then a moment later the neurons for red and the neurons for square would fire at the same time, and then back and forth. Okay. So that's an interesting idea. It's been around for a while. There's a number of variety of different forms of it. The one that's sort of being depicted here is sort of based on the LISA algorithm that was published in the 1990s. That sort of fleshes out this idea. There's and shows, okay, and then if you want to sort of expand it and extend it on things, then you could do things like you could have other groups of neurons that are perhaps sort of somehow associated with these groups, so that if these ones are firing at the same time, then that can cause these to fire at the same time. And now if you've got those things synchronized nicely, then maybe you could now sort of have neurons that represent this whole proposition that dogs chase cats. You don't necessarily need to go up that way, but it's one particular approach for organizing these things. So that's just sort of fleshing out the idea. It definitely addresses the binding problem, that it has these, this is a way of representing a complex thing and keeping the different parts separate, because we've got this temporal and specifically making the claim that we're keeping it separate by alternating them in time. So that's great. One thing I want to point out about it is that this is a localist representation. By localist, we're meaning that there is, whatever it is that is happening that is representing cat, the easiest way to think about it, or the way it's being phrased, is that, okay, I have some neurons for cat, I have some neurons for dog, and those are separate neurons. Maybe there's a little bit of overlap between them. There might be some, that complicates the story if there is some overlap between them. But conceptually, we're keeping these very, very separate. Okay. And it doesn't address all of the problems. It's sort of unclear how it addresses the other, the problem of two. How do I make sure that, if dog is in two different parts of the sentence, so dogs chase dogs, then how does that group get synchronized twice? Maybe it just fires at both times. But in any case, it's also really difficult to have, well, what's the mechanism whereby that synchrony is maintained? Okay. So what is it that's causing these things to fire, or maintaining these things to fire in this regular pattern? One approach to making them fire in this regular pattern is you're like, oh, okay, well, maybe I just have this sort of another group of neurons that, once these ones start firing, they'll sort of oscillate back and forth. So if these two, if the dog and the chasing neurons are firing, then that causes this one here. This is a group of neurons that represents dogs doing chasing. And then this can sort of go back and forth. So these ones can stimulate these, and these can stimulate these, and that maybe can maintain some synchrony over time. The difficulty with that particular solution is that now I need a large number of different neurons here. We start getting this exponential growth in the number of neurons that are needed, and you very quickly need more neurons than exist in the brain. So we need some other mechanism to maintain this synchrony, and there hasn't been a strong sort of candidate in order to have that happen. So that's a difficulty. I mean, it's not a knockdown failure. There's all sorts of things you can still do with this sort of theory, but it is sort of pointing out a limitation that would be nice to be resolved. It's also kind of unclear about how you do reasoning over these sorts of structures. So this sort of runs into the problems. But it's a really pervasive idea out there of this idea of having some, using the timing patterns in the brain to separate out ideas. Okay. All right, so that's one approach. The scaling problem, I think, is the one that really causes this problem. It's just, I don't know what mechanisms can do this without causing this giant exponential scaling of different subpropositions. Okay. There's been attempts to address this. The neural blackboard architecture, I think, would be another interesting approach in this direction that was specifically trying to cut down the number of, cut down this exponential growth. And the way they did that is basically by building almost a temporary variable structure out of neurons. So basically what you could do with this approach is they would have groups of neurons for all the basic nouns, and maybe groups of neurons for all the basic verbs, and other groups of neurons for all the basic adjectives and adverbs and whatnot. And then they had this really cool sort of grid structure where each element in this grid is actually this small little neural network that they sort of hand designed, and each of these are supposed to be sort of one neuron. They didn't bother with spiking neurons. They're just like, okay, look, let's not do all the problems at once. Let's see if we can just make a little neural structure that can temporarily bind, if dog to the noun one, and then all you needed to do is now you only need to make these sorts of pairwise connections between a small finite number of things. Okay, so basically you now only need to have, I can think of 20 different nouns, 20 different verbs, something like that. And I can do this exponential growth of any one of these 20 agents or 20 nouns. There's different roles for the different nouns in the sentence. Any one of these 20, an agent is the thing doing the action. I can temporarily say, okay, car is currently agent 20, and we do that just by changing the activity of some of the neurons in here, and it will sort of maintain that over time. And then if I want now, okay, now hold on a second, now car is not agent 20, now I want mouse to be agent 20, then I would sort of stimulate the activity of some neurons in here, and that would change this temporary binding. And then once I've got those, now I can do my exponential growth problem goes away, because now I have some finite number of things I can bind together. Okay, really cool architecture. Some very interesting hand designing of these different points just in order to try to make all this work. I think we've got the reference down in here. Yeah, this is Van der Velde and de Camp, 2006. Cool. Definitely way fewer neural resources than the Lisa. They gave definitely a story for all 4 of Jack and Doff's challenges. It also has this neat aspect where it's like, well, hold on a second. Well, because we've got this limitation here, maybe that's why sentences can't be arbitrarily complicated. Like, yes, grammatically you could make an infinitely long sentence, but nobody does because no one can actually process that. And so there's sorts of limits as to how sort of what reasonable sort of sentences and concept structures might be, and maybe that's related to how many of these things there are. It's still got this sort of localist representation nature over here, but at least we have whatever neurons are doing these sorts of things. At one point in time, these neurons are related to catness. Another point in time, they're related to mouse or desk or some other noun. So that's got some interesting structure there. Difficulties. This is a really interesting structure. Very hand designed, very nifty. Doesn't look like anything anyone finds in biology. I mean, it might just be that we're looking at it in the wrong way, and maybe there are ways of doing it, but it definitely doesn't seem to match well. It's not clear what happens, like, if this particular neuron dies, does that kill the whole system? How sensitive is it to that sort of thing? It still needs a fair number of neurons. If you want to have sort of human-sized vocabularies and represent fairly simple sentences, so like sentences of like 8 to 10 words, we're starting to hit still something like 500 million. We're not. That's less than is in the whole brain, but it's still a big chunk of the brain. And it was very much focused on, okay, that's just the neurons needed to represent any of those sentences. I still am going to need, well, what are the neural structures that let me control this and turn this on and off and do reasoning over these things? So, interesting step in the right direction, still a little big. What else can we do? Another direction that had been played with, in particular by Smolenski, I have to keep looking over in my notes in order to figure out what years these things were happening. 1990s. So sort of, this idea has certainly been around for a while. And this is, let's take a very different approach. Okay. So the particular thing we're going to abandon now is we're going to start saying, well, hold on a second. This idea of I have a particular group, one group of neurons for dog, another group of neurons for cat, maybe, animal and whatnot. There's very little evidence of that sort of thing in the brain. Okay. And it would seem to have some weird things, like what happens if those particular neurons die? Do you suddenly, are you now unable to think about cats? And that's not something there's some interesting neurological disorders out there, but we never see something like that specific. There are some really cool things out there where, people all of a sudden have difficulty thinking about constructed objects, or have reasoning problems around topics like that, or recognition problems. But nothing that seems to be like, okay, I can think about dogs, but I can't think about cats. That just doesn't seem to happen. And so one alternate approach that has sort of been sitting around in the background, or different people have worked on, is this idea of, well, all right, instead of thinking about concepts as, yes or no it's a dog, yes or no it's a cat, yes or no it's a mouse, let's represent concepts using vectors. Okay. Again, this is sort of way before the neural engineering framework stuff. This is just flat out, they're just trying to come up with ways of doing interesting things with concepts. And the idea is going to be that I might have a particular vector that means dog, or a particular vector that means blue, and another vector that means square. And then if I wanted to represent blue square, right, then I could do some mathematical operation on those vectors and come up with something that is a representation of blue square. Right? So if this one was representing blue and this one was representing square, I could do this math, the outer product between the two, right? And that would give me well, it's not a vector anymore, fine, it's a matrix, that would represent blue square, right? And then if I did the same thing with, red triangle or any other sorts of combination, just by defining the individual components, now all of a sudden I have a way to represent any combination of those components. Okay? And the only thing I need to do is be able to represent this matrix. Okay? And now, of course, I can sort of extract things back out. I can, no information is lost when I do this, ish. And I can go ahead and then, all that information is still there. Okay? And I can find out, okay, yes, is this, maybe I could do other manipulations on this combined representation. There's a bunch of different operations I could do. Outer product doesn't seem, turns out actually to, sorry, the outer product version does lose information. The tensor product, though, doesn't. So you can end up, like no information is lost. You can always recover what those inputs were from this. And now all of a sudden, you don't need, I don't need to have a representation of every single possible combination. My growth in the amount of neurons, or the size of the representation, is no longer exponential in how many concepts I'm combining. Instead, it's just increasing based on just how big these matrices are. You don't have to make the matrices to be particularly big. So lots of stuff we've been doing showing how that sort of approach could address Jack and Dawes challenges and things like that. But as you combine more information, this gets really big. So scaling is d to the n if you have n recurrent binding operations. Which again, maybe that's fine. Maybe that's why humans have difficulty with sentences like Anne knows that Bill thinks that Charlie likes Dave. Like maybe we just don't go very far in that deeper direction. Right? But they did all sorts of interesting things showing that all the sorts of manipulations that people wanted to do with these sorts of normal sort of logical reasoning things, how you could do that with this sort of vector approach and tensor product approach. Cool. Still doesn't really solve, because we still have this scaling problem. And so, and again, how are we going to control all of this sort of stuff? All right. None of those are the approach that we're going to be taking in this course. Right? That's more all sort of background of where people were thinking about, so sort of background leading into where we're going to get to. And one thing that I think I want to highlight, or that sort of comes to mind for me when looking at those three different solutions, is they were all solutions that were trying really, really hard to exactly map symbolic architectures onto neurons. Right? They wanted there to be, all of the things that we can do with this sort of high-level representation. They wanted to say, look, okay, we can just take all of those things and implement those in neurons, and the fact that it's implemented in neurons doesn't matter. Right? It's just sort of, we can still do exactly the same manipulations that the AI sort of people really want to do at this level. Okay. And one way to think about that is that we're treating neurons as sort of, this is just purely about implementation. In the same sort of way that when you're doing computer science, I want some sort of high-level programming language. I don't care about how, the plus statement is implemented on my particular computer. Right? I want that's an implementation detail. I do not care. I don't, I just want to think about this as a plus sign. And I think one way of thinking about that is this is sort of this top-down approach. We're taking high-level cognitive architectures, mapping them onto the biology, and I think a background hope might have been that here's a situation where those low-level neural implementation details really don't matter to my high-level theory. Okay, because the high-level theory needs to do stuff like this, and so I should be able to sort of continue thinking about things at this sort of level, and not have to worry about the neural. I mean, it'd be great to have the neural implementations. That would make me much happier. But I think an aspect of the hope was that the neurons don't matter. Okay? And certainly when I was doing that, I was either like, so all of my PhD time, I was doing this, these sorts of high-level things, like at this level. And I was very much just taking the approach that, look, somehow this stuff is going to get implemented in neurons. I don't know how, but this sort of type of logic sort of thing is the best game we have in town for representing language and representing reasoning. So if I'm going to do research on human cognition, I'm just going to have to use this stuff. Okay? And leave the implementation details till later. That was sort of my hope. But there was a small group of people that were actually sort of building up off, among other things, off the Spolensky approach here, that ended up taking things in a slightly different direction that is going to, I think, fit a little bit better here. And what this approach is going to be is we're going to start saying, there's some really nice ideas about this sort of the Spolensky approach, where we're taking concepts and we're turning them into vectors, and that's actually fairly a pervasive idea in lots of cognitive modeling. But this sort of binding by computing the tensor product, maybe that's overkill. Okay? Yes, using the tensor product means that I'm not losing information at all. Okay, and then that's what lets me exactly implement this sort of really complex structure, these sorts of things. Maybe I don't need to exactly implement. Maybe an approximation is enough. And the idea is going to be, all right, let's stick with vectors of a particular dimensionality. Okay. So when I pick my vectors of some dimensionality, all right, we're just always going to stay with that. And that when I bind them together, I don't want this growth thing to happen. Okay. So I want a binding operator, some sort of mathematical operation, where I can take a vector that maybe represents blue and a vector that represents square, and I combine them together, and it's going to give me a new vector of the same dimensionality as these two. Okay. The reason I wanted it the same dimensionality is I don't want this explosive growth of the more complex I make things. I'm going to need to represent larger and larger vectors. So I want that operation. I also want whatever this binding operation to be, I want it to be at least approximately reversible. Okay? I know it can't be exactly reversible because I'm losing information here. Right? I've got d-dimensionality, combining them together, I'm getting something with d-dimensionality. Information is being lost. Okay? But I want some sort of operation where I can at least approximately recover things back out. If I bind x with y, and I bind that with some inverse, or perhaps there's an inverse binding, either way, whichever way we want to write that, then I want to get back approximately my original thing. Okay? And that's going to be because, when I'm bind vectors together, I want to be able to sort of extract them back out again. And another interesting property that I'm going to want is I want this new bound vector to not be similar to either of my original vectors. And the reason I want that property is I'd really like it if when I combine multiple things together, they don't end up interfering with each other. What do I sort of mean by that? Yeah, okay, well, maybe that'll make more sense after these next examples. All right. If I had that sort of operation, what could I do with it? So if I wanted to represent some sort of the successor of 8 is 9, again, I've written this text wrong, but whatever. Then I might, I have some vector that means 8, some vector that means number, some vector that means 9. I'd have a vector that means 1 and 2 and 3 and 4. And then, I could, if I wanted to represent, one way I might represent that the successor of 8 is 9 might be, say, this sort of math. And again, you do this math, and I get this new vector. It's the same dimensionality as the original vector. Okay? This plus is, in the examples that I'm doing here, element-wise addition. So just normal vector addition. It doesn't necessarily have... There's a variety of different methods out there using different operations, but pretty much all of them use vector addition for the plus sign. We'll see why in a moment. But, I could combine things like that. I could say that the dog chases the cat. I could do something if I wanted to represent that. Again, lots of different ways I could do it, but I could do something like there's a vector for dogness, or there's a vector for dog, a vector for being the subject of a sentence, a vector for cat, and a vector for being the object of a sentence, and a vector for chase, and maybe a vector for being the verb of a sentence. All right, and again, I can do this math. I'm going to get a new vector, and that's going to be the vector for dog chases cat. And again, since this binding operation doesn't make the vector any bigger, now I can do also things like Anne knows that Bill thinks that Charlie likes Dave, having just sort of this chaining of things and going deeper and deeper and deeper with parentheses. Okay. How do we know that it's safe to think about that as a representation? Maybe we're just doing some math on things and like, okay, you end up with a final vector, but can you do anything with that final vector? Yes. So here's an example. So suppose I do a blue square and red circle, and maybe I represent it this way. Blue square plus red circle. And I have that vector, that's the vector, it's just x. Okay, and I just have that vector lying around. That's the, I've got that vector in memory. And now I want to say, okay, well, what object is blue? Okay, if I want to do manipulations on this sort of vector in order to find out what I want to extract this information back out. If I can't do that, then it's not a representation. But with the mathematical things that were noted before, if there is some sort of, so if I take this thing here, that's x, right? Okay, that's just the vector x. And then I convolve that, I bind that with the inverse of blue, right? Because we've assumed that binding has some sort of inverse. If I do that, and if I have all these sorts of general operations that are certainly there, as long as I've chosen an operation that will sort of do that well, if I've chosen operations, we're also going to make sure that these operations sort of do the expected things across parentheses in addition. So that operation there is going to be, I can bring that inside. Again, in the actuality, the only thing I have sitting around is the vector x. The only thing I'm going to do is take x and I'm going to bind it to the inverse of blue. Okay, but because I created x in this way, what's going to happen, if I go follow through this math, is I'm going to get a vector that's similar to square, right? Because that blue is going to cancel out with that, and so we're going to have something like, that is just exactly the approximately reversible property. Okay. But then there's going to be this other term, which is going to give me something else. But because I've also said that the binding operation gives me things that are dissimilar to components, this thing here, it'll be some vector, but that vector, whatever it is not going to be anything similar to square. Which means that this resulting vector is going to be pretty similar to square. Okay, and by similar, there's lots of different ways I can measure it. The simplest one could be the dot product. Right, so if I have some random vector here, right, the dot product of the random vector with square is going to be near 0. As long as the dimensionality of these things are high, it's going to be some random other vector. We're going to end up with the vector for square plus some noise vector. But whatever that vector is, it's going to be pretty similar to my original vector square. So if I wanted to do some sort of, if I actually wanted to get this exact vector out, I would need some list of, okay, here's my valid answers. Go and compare my output to each of those valid answers, which they end up calling a cleanup memory. But that's the sort of chain of reasoning of how you can do manipulations with this style of representation. I can encode information, I can extract information back out. And when people started exploring these sorts of operations in these sorts of compressed space, so that's one really important aspect of this style of representation, is we're compressing information because I'm maintaining the same dimensionality. So whatever the vector, if this is a 64-dimensional vector and this is a 64-dimensional vector and this one, the end result is still a 64-dimensional vector. That means we're compressing information. And the hope is we can choose particular operations for binding and inverse such that we get a graceful degradation of performance. Okay? Such that as you make your sentences more complicated, you gradually get more and more error, probably in the form of, okay, these things start being not, less and less similar to what we're hoping for. Okay. So that's this is a direction of research that people have been working with, sort of 90s, 2000s. A whole bunch of different operations were sort of talked about. XOR as a possibility, and some of them element-wise product, so the Hadamard product, which is just element-wise multiplication. One that was first really pushed by Tony Plate in, I think this is 1997, was circular convolution. Turns out to be an interesting operation for this. Okay. What is circular convolution? Yes, it's the same circular convolution that you run into in math class, if you have. If I actually write it out, it's, all right, I'm convolving two vectors. We're sort of doing the pairwise pairwise multiplication of everything, but this first term is this times this, plus this times this, plus this times this, plus this times this. So on one of these we're going down the chain, and the other one we're starting here and going up and wrapping it around. And we're just multiplying all those pairs and adding them together. That gives you the first element. Multiply these other set of pairs, add them together, you get the next element, and so on and so forth. You can also think of this as a compressed version of the outer product. So if I was going to do the outer product of these two vectors, and I would get this giant matrix, and then I can compress this matrix to this by sort of adding along the diagonals. So it's this plus this plus this plus this. That gets me the top term. This plus this plus this plus this gets the next term, and so on and so forth. That's the definition. The fact that it turns out that you get some pretty good approximate inverses is kind of neat. The approximate inverse turns out to be taking one of these, taking the thing you want to take the inverse of, keeping the first element the same, and just reversing the orders of the rest. That turns out to be the approximate inverse, as long as your dimensionality is reasonably high. So there's some cool math, and Tony Plate did a lot of work sort of showing that you can do a whole bunch of interesting operations with that work. He called this holographic reduced representations. We can get some sort maybe of intuitive sense of how this works. So if these were my vectors, if this was one of the vectors and this is my other vector, and instead of having a randomly chosen vector, I've got a vector that is these two images. Just to get some sort of sense of what addition does in this sort of domain, if I have this vector plus this vector, I get this vector, which is sort of kind of similar to the kitty cat picture, and it's also kind of similar to the, I don't know, penguin or whatever the heck this thing is. No. And by similar there, I mean the dot product between this and this would be reasonably high, and the dot product between this and this would also be reasonably high. And that's going to be generally the case on average if these are sorts of randomly chosen vectors. Right, so for most choices of x and y, the dot products are between this resulting thing and x, and the dot product between this resulting thing and y are both going to be fairly high compared to the dot products with other sorts of vectors. If I do the circular convolution of these two images, I get this thing, which is just sort of, all right, it's some blurry mess. Right. If I take this and I do the unbinding with this, I get back a vector that is kind of similar to this, again by dot product. So we're losing information. We're definitely losing lots of information here. So this is not exactly the same as this, but it should be similar in terms of dot productness. Okay, we've got sort of this dark area, got some bright stuff over here, and so on. It's certainly the case that if I had to choose, this thing is way more similar to this than this. Okay. And similarly, if I do the unbinding with the inverse of this, I get this shape, which is way more similar to this than this. And then you can play interesting games. Then you can say, all right, how big can I make this? How many different images, because in practice, I'm not going to be doing this with images. Images are a horrible idea. I'm only using images as an example to sort of maybe get some intuitions as to how these vectors manipulations are going to work. In practice, what we're going to just have is some random vector for dog, some random vector for cat, some random vector for mouse. Right? And then we can do this binding, and then we can sort of see, all right, how well can we recover things back out? Okay. And we can say, okay, this resulting thing, it's, okay, it's fine, it's similar to this. Is it more similar to this than any other concept in my knowledge base? And one of the really interesting things is that as long as you've got something like a 512-dimensional vector, and if you're sort of randomly choosing your vectors to mean dog and cat and house and whatnot, if you have as many terms as there generally are in human vocabulary, which is somewhere between 60,000 to 100,000 words, this approach works fine. You can encode you can encode that information, you can cover that information out. The resulting thing is more similar to your actual target than anything else. All right, what else did I want to say about that? Right, this general family of things, I forgot to actually give it the name. The general family of things is called vector symbolic architectures. That name was coined by Ross Gaylor in 2003, just to sort of encapsulate this whole family of different things. The particular choice of using addition and circular convolution as your two operations, that's originally sort of very focused. Tony Plate, in his holographic reduced representations, was sort of the first person to really push that. Yeah, and it is going to be the case. The addition and circular convolution are what we're going to be using. Circular convolution. Anything else I wanted to say about this? Oh, one of the reasons that we're going to be using circular convolution is that there's two different ways of implementing it. So this way of implementing it, so we've done a whole bunch of stuff about you can use neurons so neurons can represent vectors. Yes, great. Okay, we are all set for that. This whole theory is based around representing vectors. So cool. But we need to be able to do certain operations on those vectors. And so one big question is going to be, is circular convolution an operation that neurons are going to be good at computing? Okay? Because we just had all this stuff about, look, yeah, neurons can approximate any function, but they're going to be good at approximating some functions and not good at others. And one sort of rule of thumb was we're going to be good at doing functions that are well approximated by low-degree polynomials. Now, one cool thing is this operation is just pairwise multiplications and additions. Okay? These are all things that neurons are really, really, really good at. Okay? So that's a really good sign. But we can actually even go even better than that, because hey, there's a lot of pairwise multiplies I got to do here. If these two things are 512 dimensional vectors, then now I've got to do 512 by 500, whatever, 500 by 500, so that's like 250,000 multiplications. So that seems like that might scale badly. But there's a shortcut. The circular convolution, if you go and do that as a function call in whatever your favorite math library is, it does not do it this way. Circular convolution can also be written as the discrete Fourier transform, element-wise product of the discrete Fourier transform. So I take the discrete Fourier transform of my two inputs, do the element-wise product between those inputs, and then do the inverse discrete Fourier transform. Discrete Fourier transform is a linear operation. Neurons are definitely, that's easy, right? The discrete Fourier transform is exactly the same difficulty as the identity function, just because it's, we would just decode out the identity function, we can just put in that extra multiply right in there. This is easy. Okay. Element-wise product, cool. Well, now I only need element-wise product among the number of elements in the discrete Fourier transform of each of these components. Okay. Which is, if X is 512 dimensional, then the result of the discrete Fourier transform is also 512 dimensional. It's not quite that nice and easy because the discrete Fourier transform gives you complex numbers. So that means instead of 512 numbers coming out, I've got 1024 numbers coming out. But then there's also some symmetries because the discrete Fourier transform gives you, because X is real, and so the discrete Fourier transform, there's going to be some interesting symmetries in the output. Fine, so basically that cancels out. All right. But this just ends up turning into a bunch of element-wise multiplies. Okay, and then the inverse discrete Fourier transform is also linear. Okay, so so the only thing that neurons actually, the only thing that's nonlinear that neurons need to compute to do this whole thing, all right, is if I've got 512 dimensional vectors, it's something in the order of 512 pairwise products in order to compute all of this, and everything else is just linear operations. Awesome. So that's going to make it really, really efficient to go ahead and implement this in neurons. Okay. And that was one of the reasons why when we were building, so when Chris Elias Smith, so the person who invented the neural engineering framework, was trying to really want to say, okay, is this also a solution for how do we do language manipulations? He came across Tony Plate's work and went, okay, this is perfect. This is exactly how we want to go and implement these things. Okay, so it just jumped out. Let's steal that math. Go ahead and do that. Okay. So that was sort of this nice convenient. Someone had already worked out the math. Let's go ahead and do that. Okay. Cool. So this ends up with a much more efficient way of building things. It means that we can represent all of those sentences in something like 80,000 neurons, like way fewer neural resources than any of the three other earlier examples that we were showing up. So like 1,000 times less than the neural blackboard architecture. Really, really nice approach for going ahead and implementing that. And one really important thing is we are not having the neurons be a mirror implementation. So what I want to highlight is that we're not ending up with something that is exactly the same as this initial symbol stuff. Okay? So it's not a perfect implementation of the high-level logic that people are used to thinking of. Okay? One aspect of that is certainly this: as you make your phrases more and more complicated, the chance of it being able to accurately decode things out and extract out the individual components ends up dropping. Okay. So that's sort of, it's nice that it's sort of a soft, smooth sort of thing, but that ends up being a little bit of a, so sort of a little bit of thing to keep in mind. But the thing that I think really convinced me that maybe we're on the right track here is not that we just ended up with, okay, so it's sort of, all right, the neurons are just doing a bad version of the high-level reasoning stuff that people are wanting to do. Cool thing is that maybe once we've done this vector stuff, maybe now we get new capabilities that wasn't something you could do with the high-level reasoning. Okay. And we've got one pretty strong example of that. Okay. All right, so what is that example? So there's a standard test of fluid intelligence. And this is called the Raven's progressive matrices. This has been used in psychology for ages as an attempt to test fluid intelligence, which is supposed to be the intelligence that isn't, oh, I've memorized the answers to lots of different types of problems and I've practiced really hard and on tests and I've studied for exams. None of that stuff. What we're trying for is problem solving in novel domains where you just need to be able to do reason. It's one of those attempts at sort of finding a measure of intelligence that is sort of not strongly dependent on practice and reasoning, or on practice, and is more sort of inherent to the individual. The actual form of the Raven's progressive matrices I'm not allowed to show because it's one of those things where if you've seen the problems, then if you're ever given this test in the future, then now you've had practice on it. So I can show you problems of the same form. Okay. And so here, for example, is one particular form. It's generally, it's a 3x3 grid with one square missing, and your challenge is find me what goes in that square. And generally what's going to happen is we're going to give you 8 possibilities, and you're going to choose which one goes in that square. Okay. And that's all we do. Okay. And for some of them, it's really easy. So my hope is, well, I can't come up with any reasons for anything else. But yes, so this one, 555 seems like a pretty natural thing to put there. Okay. The actual problems themselves actually tend to look like this. Instead of being number-based, they tend to be shape and pattern-based. Again, one can sort of stare at that and figure out what the right answer should be. And sometimes they're a little bit, things like that. Okay. And this is a sort of problem that people had tried implementing in terms of, okay, how would you build up a system that can solve these sorts of problems using the general sort of symbol manipulation approach like this. Sort of represent, just good classic AI problem. And basically they ended up failing at this task. Okay. Or at least, I mean, not failing. There was a good computational models out there. There's definitely published models. Most of them were based around the idea of, well, maybe what's happening when people solve these tasks is there's some database of types of patterns that's sitting around in your brain, and you go through and sort of see, is this one of those types of patterns? So maybe I have the type of pattern of duplicating an item and keeping on adding one. Oh, okay. All right. So that was a possible pattern. I go look at this. Yep, that one, it matches that. Yes, that's in duplicating the last item. Yep, this. So if that works for all of these, then this one should be 5, 5, and duplicate whatever the previous one is. Okay. And maybe you've got some list of 100 of those sorts of patterns, and you just sort of apply that list and come up with the next one. Okay. And that model, that sort of computational model, I guess, sort of works in this task. It's a little unsatisfying because the whole point of this test was to be a test of fluid intelligence. And that seems like, no, it's just you've got this database of patterns and you're just applying that. And so that looks exactly like the, oh, I've studied lots sort of solution, which seems sort of wrong. So this is one of the tasks, that I have forgotten to actually get the link to. So I'm going to go ahead and pull it up on YouTube. So CTN Waterloo. Sorry about this. Yeah, it's one of these videos. Give me the videos. It is, nope, complete a pattern. There we are. Sorry about that. No, get rid of the ad. Get rid of the ad. There we are. All right. So here is a model running in Nengo, where we are going to be presenting it exactly that same problem. Okay. We're going to give it, now in this particular place, we've actually gone much farther. We've actually said, okay, we're going to do everything in this task in neurons, right from all right, we're presenting the input as visual stimuli. We are doing the output as muscle contractions on an arm in order to draw something. So this is sort of, we're doing absolutely everything in neurons. The motor control stuff, you can sort of imagine, okay, that's kind of like, control theory is designed, differential equations are designed for doing motor control stuff. It's what people do with them. So you can imagine that you can take motor control type tasks and implement them using the differential equations that we've seen in class. Visual recognition, fine. We're sort of used to the idea that people can use neural networks to classify input symbols. It's the rest of things that are a little bit of a challenge here. But again, we're building it all up out of the vectors and functions on vectors and differential equations of vectors that we've seen. And we're going to show this particular example. We're just going to show it to the individual elements one at a time. We're putting some little triangles in there, just sort of okay, I'm going to the next example now. Fine, whatever. And I'm also just showing the whole thing down here, just so you can actually see the input. This is the first time it's seen this example. I say a question mark, and it writes out 555. How does it do that? What's going on here? Okay. Well, yeah, let's skip right down to here. So, here's what the system ended up doing inside in order to solve that task. A whole bunch of, we'll worry about the coordination task. How does it know, like, to do this step first, and then this step, and then this step, and then this step? We will deal with that again in another lecture, the one on action selection. But what's the underlying math that it's going to do? Okay. And here's the underlying math. So first of all, I need a representation of each of those individual components. So I need a representation of this square, and this square, and this square. Okay. How are we going to do that? Well, we're going to have a vector that means each of these numbers. I have a vector that means 1, I have a vector that means 4, I have a vector that means 5. Okay. Since I'm going to have multiple items in a square, I need some way of representing sequences, something like that. So I'm also going to have vectors that mean position 1, position 2, position 3, and so on. So that means this top square here is going to be a 1 in position 1. This one here is going to be a 1 in position 1 plus a 1 in position 2. So sort of approach is going to give me a vector that represents each of these sequences of symbols. And it's just a new vector. Okay. Now these might be vectors the system has never seen before, right? But that's fine. I mean, we've been building in class neural populations that can represent any a vector of some dimensionality. We don't have to have trained it on every single possible vector. We're just implementing, like, here it's, this is a group of neurons that can represent a vector in some range. So fine. We can represent things even if we've never seen them before. Some new novel pattern. All right. And I can do that. I can build this all up. Okay. Fine. I can have groups of neurons. I have some vector that means each of these things. Okay. But what I really want is to have some sort of vector that means the transformation from one to the other. Well, I've already got an operation that means sort of transformation. I've already got this binding operation around. Let's just use it. So let's say that I take, if I take C2 and combine it with C1, the inverse of C1, that's going to give me a vector that if I had taken that vector and applied it to C1, I would get C2, approximately. Okay. So this is now a vector that represents the transformation between two lists of symbols. Okay. That's not something that's natural to do in the normal symbolic approach. Normally, if I was representing these things as a chain of symbols, it's trying to represent what is the transformation from one chain of symbols to another is definitely a little tricky. Okay. And there's different ways of doing it. Certainly people have tried that, but this is sort of one that just falls out of the components we already have. Okay. So I have a transformation that means a vector that means the transformation from this to this, and another vector that means the transformation from this to this, and so on and so forth. So I have a vector for this transformation, a vector for this transformation, this one, and this one. So that's 5 different transformations. So what am I going to do with those vectors? Well, they're all just vectors. I could take the average. All right? That's a thing I can do. So that vector there, that vector that I get that is so this is now a vector that represents the average of 5 different transformations between 10 different symbol structures. And now I can take that new vector and I can say, all right, let's just apply it. Let's bind it with this and see what happens. And if you do that, you get a new vector. Take C8, combine it with that thing, and it turns out that you get approximately the right answer. And by approximately, I mean it's closer to the right answer than anything else. So, it's not exactly this vector because it's got the same sort of noise properties that we'd sort of seen with all the other extractions. That's a very different solution. That is a thing that's not a standard way of doing processing. In terms of like normal symbol manipulation. So this is saying that the system we've described here is not the same as a standard symbol system. So this is partly why we tend to call these symbol-like operations, and it's a symbol-like framework rather than symbols. This is not quite following the technical definition of what a symbol is. In fact, we can start doing weird things like that. One caveat I will note is this only works if we've defined the vectors that mean 1, 2, 3, 4, and P1, P2, P3, P4 in a certain way. And the way that we do that is this sort of thing. We end up saying that the vector for 2 is not just some randomly choose. So we randomly choose the vector for 1. Okay. And then we say, okay, the vector for 2 is just going to be the vector for 1 bound with the vector for 1. And the vector for 3 is 1 combined with 2, or 1 combined with 1 combined with 1. Okay. And the same thing for position 1, position 2, position 3. Okay. So we need that way of defining things, and we also need that we don't want that when we do this binding, we don't want, because we're going to represent this all in neurons, I really don't want the magnitude of this vector to start growing exponentially. I'd really like everything to stay as like unit vectors, say. Okay. And there is math that lets you choose this basic vector in such a way that when you bind it with something else, the vector, the length of the resulting vector doesn't change. It's called a unitary vector. So fine, mathematically defined. Basically, the way you get it is when you do the Fourier transform, you want the radius of the complex numbers to always be 1. But whatever. Technical details as to how to define that. So those two small things, basically that just stops this from causing an exponential growth in the magnitude of the vector, keeps everything as unit length. And that's going to mean that the neurons are still good at representing them because we can build up our neurons to represent vectors within some unit sphere. Okay, that was a lot of weird stuff. What I'm going to yeah, in the lecture notes, I won't go through these. It's fairly straightforward to go ahead and do these sorts of manipulations. So the fact that there had been this whole group of people, Tony Plate, Ross Gaylor, yeah, there had been a community of people working with these sorts of operations, seeing, okay, this is how these things address Jack and Dawes challenges. Indeed, the 2003 paper where the term vector symbolic architecture was sort of first popularized was explicitly here's how any of these things will deal with Jack and Dawes 4 challenges. Basically, as long as you've got mathematical things with those operations, you can go ahead and deal with all of those problems. I will say that I think there was kind of a resurgence of this sort of work in the 2000s, 2010, in the last 20 years. I don't know, I mean, really the only thing novel that we've been doing with these sorts of things is pointing out that, hey, these operations you can implement in neurons and it all still works as you hope. And so that's been sort of a part of this maybe resurgence. If you are looking for other people that are doing these sorts of approaches and maybe not dropping all the way down to actually using them in neurons, but are just sort of, let's look at these sorts of vector manipulations on their own. The two that really jump out for me are Michael Jones' work. He's out of Indiana University. So that's one that I would look at. And then the other one is Alex Kelly. They've been doing some really cool stuff with connecting this to distributable, connecting this back to the architecture of how memory might work. And they are now just got an appointment at the Carleton University in Ottawa. So they're doing all sorts of interesting things in this direction as well. Excellent. So that's the approach that we're going to take to symbol manipulation. The main thing I want to add on to this is, so there's that same reasoning that we were going through before. The main thing that I want to add on to this is all of this can be built out of the components that we've already seen. But one interesting challenge is going to be, we are now starting to talk about things at a really high level of abstraction. Okay. And we're going to want, so all of these operations I can just define are all things that I could build functions out of, and then we can go build things up. But now we're going to need to start giving ourselves some new tools in order to explore these capabilities a little bit. What tools do we want to do? One of the nice advantages with Nengo as a software package, and that's what we've seen so far, is, all right, we've got the software package that lets us sort of define these things. Now, since it can define these core components, well, then we can build libraries on top of Nengo that can maybe help us build up these more abstract things. Okay. And we have been working on, and we're building up one for doing this sort of modeling. Okay, so I want to give a brief introduction to that and also use that as an example of sort of a refresher of what we just learned in this lecture. So the way this works, if you pip install Nengo SPA, what is SPA? This is what we're calling is the semantic pointer architecture. So while the vectors that I was just talking about, the original term for this operation of using addition and circular convolution, the original term was holographic reduced representations. The work coming out, we've been taking that core math and then pushing it in very different directions. So one way that we've been pushing it is implementing in neurons, and the other one is building up a family of tools for manipulating, building up a full cognitive architecture out of these components. Okay. And so we've given a little bit of a name change. So we're calling the individual vectors, we're calling them semantic pointers. We'll get into a little bit more about why we might want to call it that way. Basically because of this compression aspect, this extracting information and then recompressing information. We're sort of alluding to the idea that you can manipulate and pass around this information in a compressed form, but then you can extract things back out. Something like in computer science, you can manipulate and pass around pointers without actually accessing the information the pointer is referring to. But we're also, the reason that we're also calling it semantic is that if you, where's an example here? If I have blue, let me go back over here. If I have this sort of representation of blue circle, all right, and I have some sort of compressed so the compressed representation of blue circle is blue combined with circle. But if I then had a compressed representation of, I don't know, an aqua oval, right? If the vector for aqua is kind of similar for the vector for blue, and the vector for oval is kind of similar to the vector for circle, and again by similarity I mean dot product, then it would be kind of nice if the compressed version, though if aqua times oval, or aqua bound with oval, is similar to blue bound with circle. And it turns out that is the case with circular convolution. So basically what we're saying there is that any sort of semantic similarity, so similarity between the individual terms, is kept when you do this compression to a certain degree. So that's why we ended up calling these things semantic pointers, because the compressed version, you can still do some manipulation, some reasoning on the compressed version, just based on that similarity, without extracting information back out. So we've called this the semantic pointer architecture, and we built a library on top of Nengo that helps you do these sorts of things. So it's pip install Nengo SPA, right, which apparently I already have. And then we're going to go ahead and run Nengo, and we're going to give a new example. I'm going to call this SPA1. We're going to import this new library, and it's Nengo underscore SPA, and I'm just going to call it as SPA, just so that I don't have to type out Nengo SPA all the time. And then we're going to make this network a little bit more aware of these sorts of things by saying this is a SPA network. Okay. Yes, the SPA network is it's a subclass of the normal Nengo network, so all the things that you expect from a Nengo network you can do from the SPA network. But we've now got a couple new capabilities. So the simplest new capability is I can easily define a group of neurons that is going to represent some high dimensional vector. Okay, so we'll choose some dimensionality, let's say 64 dimensional. And I'm going to say that we can make a state. We're going to call this a state vector, basically where this is a thing that the brain has access to, a thing that the brain is representing. Okay. And we're going to say, hey, look, it's d-dimensional. Okay. Yeah, let's, instead of calling it A, let's give it a more meaningful name. So maybe this is what I'm visually looking at right now. Okay, I have some visual stimulus. There's going to be some d-dimensional vector. Okay, maybe this is like maybe this is the output after, I'm feeding in some input into a deep neural network, and the output from the network, instead of being a classification, is just maybe that second last layer from the network, which is just here's all the features in it, which is some high dimensional vector that is some representation of that visual thing. Or maybe it's gone ahead and done classification. Whatever, either way. Fine. What can I do with that? Well, it is just built out, if I double click on this and double click on it, it is just built up out of individual components that were sort of totally what we're used to. So it's not introducing any new concepts in terms of the actual system. And indeed, we can even say pull out a bunch of sliders. Right, and we can say the output is some value. All right, now let's go down to some reasonable number. This is a 16-dimensional. All right, so it really is just a group of neurons that is representing a 16-dimensional vector. Okay. We could have done that with just a perfectly normal ensemble. The only thing this SPA state thing is doing is, hey, if the dimensionality gets really big, it starts splitting it into some ensembles. That's really the only main thing that that's actually doing, as just sort of a convenience, so that I don't have to really worry about that. And the reason we split into sub-ensembles is I don't want to wait for it to solve for the decoders for giant groups of neurons. Okay. But let's just represent a vector. So maybe this is the vector that means cat, and so fine, I can feed in that vector and it represents cat. I really don't want to be moving these sliders around. That seems really boring. How do I remember that this set of sliders means cat? And looking at this plot here, what? I don't know. I can't look at that plot and say, oh, that's clearly the vector that's close to the vector for cat. Right? So user interface-wise, this is useless. So there's new graphs. In particular, one that we're going to think is really important is we're going to call this the semantic pointer cloud plot. And we're going to pull up the semantic pointer plot. Okay. What's this? So this is going to be a high-level way of me quickly interacting with and defining vectors and things like this. Okay. I don't want to move a bunch of sliders around and say, okay, that's the vector for dog. What I want to do is I just want to right-click on this and say set value. I'm going to say dog. What's it going to do? So what it does, I've typed in dog. It has no idea what a dog is. So the user interface itself is just going to go ahead and randomly generate a d-dimensional vector, so a 16-dimensional vector, and say, all right, fine, that's going to be the vector for dog now. And it's going to feed that vector into the system. And we've got this plot here, which is just plotting fine. Whatever that vector is that's coming out of the system, here's its similarity to dog, the vector for dog. That's really what I care about. I don't care what the individual numbers are. I just care about the similarity between the output of that vector and dog. And also feed in cat. Cool. All right, now I've got a vector that's pretty similar to cat, not very similar to dog. Of course, since these are vectors, I can manipulate them. I can say cat plus dog. Cool, and now I've got a vector that is pretty similar to dog and pretty similar to cat. Okay. Again, they're vectors. I could do dog plus, I don't know, 0.3 times cat. All right, now I've got something that's dog plus, and it's kind of similar to dog, not very similar to cat. This graph over here, let me actually give it a little bit. Let's do dog plus 0.6 times cat. Okay. This visual representation here, which we call the cloud representation, what it's doing is it's actually plotting the same data that's in this graph. Okay. It's using the magnitude of this dot product to be the darkness of the text, so that's why cat is sort of in a little bit lighter text, and it's using the relative ratios of these numbers to do the size of the text. So that gives a nice, so basically once you start having lots and lots and lots of terms, this graph starts being really useless because like all the lines are hard to distinguish, whereas this graph over here, it's the same information, but it's just basically picking out the important ones. That little bit of jitter that you're seeing is the same jitter that is in this graph here. Okay. Of course, importantly, one thing to keep in mind is the operations that we're doing here, right? So it's just neural activity. It's just neurons with neural activity, and we're doing some decoder that gets me out a vector. And then we're taking that vector and we're doing the dot product with these individual items. Well, the dot product's still a linear operation, so this is all still, this is like the math to do this is just, this is a linear weighted sum of the activities in the neurons. Basically, so everything in that whole chain is all linear, so these graphs are linear weighted sums of the activities inside, in the same way that all the decoders are in Nengo. Okay. But now we can represent some arbitrary things. Okay. And we could, so we can represent arbitrary things that way. Let's go a little bit fancier. So first thing I'm going to do, I'm going to go back up to 64 dimensions. Actually, yeah, let's stick with 64 dimensions. I tend to use that as a minimal default because a lot of the properties of this sort of, oh yeah, does the inverse work? It really works much better in higher dimensions. Anyway, maybe I've got a group of neurons representing this is what I'm visually seeing. Maybe I want another group of neurons representing my memory. I want that memory to be stored over time, so I want to make that an integrator. So the way I make an integrator is I connect a group of neurons back to itself with a feedback connection that is just the identity function. So there's an argument on this SPA-STATE thing that says, hey, do a feedback connection that scales it by 1. So this is now an integrator. Okay? It's exactly the same sort of integrator that we saw before. It's just in 64 dimensions rather than in one dimension when we taught it in class, and in 2 dimensions when I did that critter example that was storing its location and time. That was a 2-dimensional integrator. This is a 64-dimensional integrator. Same math, same everything, no changes to anything. I do want to be able to connect from this group of neurons to this group of neurons. For that, one thing that we've been sort of experimenting with is this SPA system has a bunch of new capabilities for connecting things together and doing manipulations on them as you're connecting them together. And the easiest of these is that. Okay. It's an interesting notation. We've been playing around with different notations. I'm warming to this one. There's certainly going to be some people, depending on your background in programming theory, where it's like, ooh, that's an interesting choice for an operation. But the intent is that this is somewhat visually reminiscent of, okay, we are taking this and we are sending it here. Okay. And that is just a connection. That's just an identity function connection. Okay. I'll show a slightly more complicated example of that in a moment. Let's get rid of that graph because we don't really need it. And I'm going to pull up a cloud plot for this one. So now what can I do with that? Okay, so now I can feed in cat. All right, my memory has cat in it, that's fine. Now I'm going to take away my input. And since this is an integrator, this is still storing a vector in it, and that vector is still saying pretty similar to cat. Okay. I could set the value to, I don't know, dog. I'm going to take that away. All right, that transitioned really quickly. I'm going to slow time down a little bit. Feed in cat. Maybe you want to slow down time even more. Feed in dog. Take it away. Oh. Now this memory thing has a vector in it that is kind of similar to cat and kind of similar to dog. Okay. And feed in rat. Okay. As it gets more and more similar to rat, why did these other ones fade away? If it was just doing math, if it was just sort of adding, okay, rat into these things, the dot product of the vector with cat and dog and rat really shouldn't change. Or the dot product of that vector with cat and dog really shouldn't have changed. It does, though, because this group of neurons is encoding a vector within the unit sphere, the unit hypersphere of 64 dimensions. The same thing that happened in the 2D case where as we were representing, as the critter moved to the far right, or moved to the right, it sort of lost its position on the X. We had a critter, it thought it was at this location, and then it moved to the right, and then it slowly ended up thinking that it was over here. Again, that was just because it was an integrator, but we hit the ranges on the integration, and so it starts losing the information. Kind of a nice feature that, hey, yeah, when you feed in information, I can either wipe out, for the first little while as I feed in information, I'm now saying, okay, represent both things. Okay, but then if I really feed in rat for a long time, dog is going to fade out of memory. Okay. and that's just a side effect of this style of representation. Sorry, it's a side effect of using neurons that are good at representing things within a unit hypersphere. Cool. So this is the sort of thing where you could then go ahead and do like, okay, well, what happens if I get someone to memorize cat plus dog plus rat plus mouse plus house, I don't know, some sequence. Okay. And then they're looking at that list, and then you take away that list, and they have to remember that. Okay, it's going to gradually decay because that integrator is not perfect. Okay. And then you can do fun questions like, oh, okay, if you have a vocabulary of a certain size and a dimensionality of a certain size and a memory, how long you're going to maintain this in memory, you can check how close is this to human behavior. Okay. And there's a variety of different experiments in that direction. 64, as you can sort of clearly see there, at 64 dimensions, it forgot a bunch of those other things, and it only knows about 6 words at this point. So 64, it was really pushing it. If I was doing 512, that tends to be the point where you're starting to get data that is sort of similar to human-sized vocabularies. Okay. There's no particular reason that we're sticking with like powers of 2. We just sort of fell into that habit. So we probably could, 500 would have been fine, 600 would have been fine. But for some historical reasons, we've been using 512. Doesn't really matter. Some sort of value in that range seems to start being human size. But it also runs much slower, so I'm not going to do that in this particular example. But that's at least one aspect of we can build up something that remembers things. But, and I will also say, if I wanted to now represent that blue circle plus either a blue circle and a red square, I can say blue times circle plus red times square as my input, and it'll interpret the times as circular convolution. Of course, if I do that, both of these graphs are going to look blank, because the resulting vector is not similar to blue or square or red or circle. So both these graphs also have an option on them to show pairs. Okay, so that's also going to include the pairwise combinations of those things when it's making the graph. Okay. So that is indicating that, oh, okay, we are feeding in that vector. So again, that's just a display thing. But just so people know that that's there. But that's me doing that math, right? That's me saying, all right, all this is just to communicate. This is just an integrator in 64 dimensions. If we really want to claim that neurons are doing this, then I need a neural implementation of this circular convolution. And as was pointed out in class, fine. That's just going to be Fourier transform, pairwise multiplication, inverse Fourier transform. So it's linear operations and pairwise multiplies. But of course, I don't want to manually write that all the time. The whole point of having software libraries is it'll go ahead and build one for me. So let's do that. I'm just going to change this example. I'm going to say that we have a group of neurons representing color, a group of neurons representing shape, a group of neurons representing memory, and then I'm going to say color times shape should be sent to memory. Okay, I've got memory, yay, binding, oh, color, binding. And it went ahead and built everything for me. Okay. Again, this is us attempting to come up with convenient ways of quickly building the sorts of things that we want to. Okay. Cloud there, another cloud there. Cool. So with that in mind, same display, same everything. Okay. If I go ahead and run this, oh right. there's a fair bit of neurons in here. There's a bunch of pairwise multiplies going on in there. 64 dimensional, so there's a fair number of different groups of neurons inside there. Wasn't too bad to build, but now I can do something like, all right, blue as a color. Again, this system has, I'm running the model already right now. I built the model. It's just meant to do this math in general. It's never seen the vector blue before, because I'm randomly generating a new vector right now that just means blue. Cool. And I'm going to set the value here. For this one, it's going to be circle. We're randomly generating a new vector for that. Okay. This here was trained up to just do, or like this group of neurons here was built to approximate the circular convolution of these two elements. It's feeding in some vector over into this memory thing. It's in that integrator. And now we have in there the whatever vector is ending up out of all of this process is pretty similar to the ideal mathematical vector for blue convolved with circle. Okay. First I can take this input away, and the memory stays. It's blue circle. Red square. Let's feed that in. Right, feed that in. My memory now has sort of both things in it. I'm going to take away this vector. And my memory has in it a vector that's pretty close to the vector for blue circle and pretty close to the vector for red square. Okay. So we can encode information, we can bind information together. Let's do one step farther. Because not only should we be able to bind information, we should be able to extract information. We should be able to query this memory. I should be able to have a vector that I can feed in that is what I want to extract out. I want an answer. And what I want is I want to take whatever's in my memory and combine that with the inverse of my query and send that to my answer. Bind query answer. Okay. Cloud query cloud for my answer. Okay. Again, this is just, when I run the model, when I build this model, all it's doing is optimizing each of these individual components for just vectors in general. All right. That's all it's building up. It's not until I actually run the model that I'm going to start generating the particular vectors that mean blue, red, circle, square, whatever. Okay, we'll just give it a moment here. There we are. Now we can do the same thing. Feed in blue. Feed in circle. Alright. Feed in red. Feed in square. Okay. My memory now has in it blue circle and red. My memory has in it a single vector, because my memory is just representing a vector. That vector happens to be similar to the ideal vector for red square and similar to the ideal vector for blue circle. I'm going to take my stimulus away. So we are now remembering that. Okay. I'm now going to query it. I'm going to feed in blue, the vector for blue, and ideally this answer out here should be circle. Blue, and my answer is circle. I can feed in circle, and I should get out blue. Right? I'm getting a vector out that's kind of similar to the vector for blue. Ask it for the square. I get out red. Ask it for red. I get out the vector. It's not exactly the vector for square, but it's more similar to the vector for square than any of these other vectors. That's what we're seeing in this sort of graph. You want to scale this up to human-sized vocabulary, you need to increase this number. In particular, if you start having a human-sized vocabulary, you do tests like, okay, well, how many things can you combine in here? With a human-sized vocabulary of 60 to 100,000 items, and 500, if you have 512, 600, maybe 700 dimensions, then you can actually store somewhere around 8 items in this memory, and still get sort of 99.9% accuracy in your recall out. Cool. All right. So that's hopefully just another way of showing. Okay, so let's build up these more complex things out of these components. All of these sorts of components, again, these state things. These are just integrators that we've sort of split into subparts because instead of having one giant ensemble for all 64 dimensions, we're splitting them into these smaller parts. So like basically a sub-ensemble for each subchunk. So that's nothing particularly interesting going on with these state components. These things that are implementing the binding operation, the things that are being implemented because of that star, they're a little interesting exactly what's going on in there. It is just a whole bunch of ensembles that are doing each of those pairwise multiplications, although done in an interestingly efficient manner. So again, if we sort of look at the structure of what's going on here, it is just one layer of neurons. Lots of different transformation matrices happening, but all of these transformations, this is all just linear operations, so we can combine them all together into one layer of weights. All right, it's a decoder times a matrix times a matrix times a matrix times a matrix times an encoder. That's what the actual connection weights are going on through this process. But it is just a layer of weights. And what we've done is just that efficient implementation of pairwise multiplication that I'd mentioned, that involves just doing squaring of one-dimensional things rather than making them two-dimensional. Whole other thing that we've talked about there, but again, it's one of the nice things where all the components are things you've seen before, already been nicely optimized. We don't have to generally worry about them, and we can start building up these sorts of larger structures. And I think this is also a nice example where, like if I print model.number of neurons, just how many neurons are in this bloody thing. So this model I was just running is 70,000 neurons. Right. It's starting to get up there pretty big. If I start doing something like 512 dimensional, which would be the sort of the size if I was going to do human level sort of vocabulary and whatnot, there we're starting to talk about 500,000 neurons. Okay. But that's 500,000 neurons to not just represent, because it's just one of these things just to represent that sentence. Okay, it's the 500,000 neurons to start binding and unbinding and doing these sorts of manipulations. All right. As opposed to, if we go back to some of these other examples in the notes, as opposed to these sorts of things that even just to represent the sentence was starting to look around 500 million neurons. That argument that, hey, we can do this sort of thing with relatively few neurons, that's, I think, the strongest argument I have. That is this actually how brains work? No idea. Okay. The only argument I can make is I don't know of another method that lets me do these operations using something like spiking neurons that ends up using anywhere close to this sort of level of number of neurons. Does it need to be exactly circular convolution? There's probably a whole family of other functions that would also work. So they should be like anything in this family. Circular convolution just happens to be a pretty convenient one to just go ahead and implement. There's probably other ones that have similar capabilities. But for right now, in terms of encoding and doing these sorts of manipulations with neurons, as far as I'm aware, this is the nicest approach. And I would love for there to be other examples to sort of compare to, but this is the approach that we've been sort of exploring and expanding on, in the lab here at Waterloo. Okay, that's quite enough of all of that. Thank you very much. One of the big things that we still need to talk about next is how do we sort of coordinate all of this sort of action. So we'll be talking about that a little bit more in the next lectures. And we will see how it goes from there. So thank you very much, and we'll see you next time.